So now we've got a tricky one. We have the voltage across the 15 kilo ohm resistor is 500 volts, positive at the upper terminal. Find the power dissipated in each resistor. We're not going to find the power dissipated in each resistor, but we'll find some of them. So anybody want to suggest a way to start this one?
Mesh?
Oh well, okay, we could. I wasn't planning on doing mesh, but we can. So let's do that. So if we do mesh,
Is
how
this where we would another one? Would we use the y delta formula?
we could use that, yeah, but I don't think you're not going to have that on your test. But yeah, we could use that as well. But I think the intent on this problem is not to make it quite. It's not necessarily to use. I mean, you can use any technique you want on unless you're told not to, but this is not just to use some of the basic ideas. So I mean, we could do mesh, we could do y delta, but I actually just want to look at this from basic principles, and then we could go back and look at it another way. So can I figure out the current through this 15 ohm resistor? Anyone want to hazard a guess if I can I figure out the current through the 15 ohm resistor?
Oh yeah, because we have the voltage already.
Yeah, we have the voltage already. So I know if I draw the current in this direction, that V equals IR. And because the voltage, I've given 500 volts and I was told which side was the plus side. So that's 500 equals I times 15,000. So I equals 500 over 15,000, which is 0.0333 amps, which is the same as 33.3 milliamps. Okay, so I know this is 33 milliamps, 33.3 milliamps. I know this current is 100 milliamps. So do I know what the current is through the 75 kilo ohm resistor?
Yeah, we can
Yes,
do
it
a
would have to add up to
KCO.
100.
Right. I think a lot of y'all were saying the same thing. 1 milliamp is going this way, 33 milliamps is coming in, and then I drew this current as coming in because I know it's going to. So I'll say I in the 7.5 ohm resistor plus 33.3 has to equal 100. Or I through the 7.5 kilo ohm resistor has to equal 66.7 milliamps. Okay, so can I now get the voltage difference across the 7.5 kilo ohm resistor? And the answer is yes, I can. So my voltage will equal IR. And so my voltage is going to be 66.7 milliamps times 7.5 kilo ohms. A milli and a kilo cancel each other out. So I can just do 66.7 times 7.5. Well, let's see. I will do and I get 500. So I get 500 volts across this one as well. What does that tell me about this middle resistor right here? So I have one resistor at 7.5 kilo ohms, and I have another resistor that's 15 kilo ohms. The voltage difference across this one is 500 volts. The voltage difference across this one is 500 volts. And I've got another resistor right here that's 4 kilo ohms. So if I were to call this ground, make that 0, relative to ground, what's the voltage right here at what I just labeled A, and what's the voltage right here at what I labeled B?
Would they both be 500?
They would both be 500. And if they are both 500, is there a voltage difference across them?
No.
No. And if there's no voltage difference, there's no current. And so there is no current through this 4 kilo ohm resistor.
And that would mean that it's dead?
No, just that there's no current through it. I don't know.
Okay.
Yeah. It's not, just the current is 0.
So it's just a wire, basically.
No, if it was just a wire, that would be a short. Well, it doesn't matter. I mean, it is, yeah, it actually, it is a wire, but it could have any resistance because there's just no current through it. Yeah, it could be a wire, but it also could be an open circuit, or it could have any resistance. It's just useless. So there's no term for that other than 0 current. Well, there is a term for it. That means this is it's called a Wheatstone bridge, and it's balanced. But that's yeah, I don't think you need to know that. But what we know is if there's 0 current here, 0 amps here, what has to be the current through the 5 kilo ohm resistor?
Negative 66.7?
No, it's still going to be 66.7 because it has any current coming through here has to go through there. It doesn't have any choice because it can't go through the middle one because there is no current there. So the current through the top branch has to be the same as this current. So it has to also be 66.7.
Yeah, but the two of them cancel out. Since there is no
It's almost
current.
like they're in series.
No,
Yeah.
it's not like they're in series. They are in series.
Okay.
Yeah, but they don't cancel out. It's not negative. It's just it is all the same current.
Oh, okay, okay.
Yeah, so it's all the same current. Similarly, on this side, that's all the same current, and that's 33.3 amps. So now that we know that, we could figure out, if we needed to, the power dissipated in each resistor. We have the current and we have the voltage. Well, we have the voltage for the bottom ones. We don't have the voltage for the top ones, but we could get them. So I will get the voltages real quick. So the voltage across this 5 kilo ohm resistor, that's just V equals IR, is 333.3 volts. And the voltage across the 10 kilo ohm resistor is also 333.3 volts. So then we could get the power. And I'm not going to do that because that's just multiplication. The power would just be P equals IV for each one. But I do want to look at the power supplied by the 100 milliamp ideal current source. I know the power supplied has to equal the power dissipated. So I could find the power dissipated in each one of these and know that equals the power supplied. But I'm lazy and I'd rather do it a different way. I know the voltage across this current source. Do you know the voltage across this current source?
It's the sum of the, I can't read it, 5 kilo ohm and 7.5 kilo ohm voltage? Maybe?
Yes. Yes. So I have this middle resistor. There was no current. It's like it doesn't even exist. So when I look at this, what we see is that these two resistors in series, so this resistor in series with this resistor, those two resistors are in parallel with these two resistors together. And the voltages for elements in series add up. So if I look just at one resistor and the other resistor, if this is 500 volts and this is 333.3 volts, then from top to bottom has to be 833.3 volts. So I would get 833.3 volts on the left-hand side, and I know even without the numbers given, I know it has to be 833.3 volts on the right-hand side because this branch is in parallel with this branch because their ends meet. Now let's look at this big picture. This current source is in parallel with this branch which is in parallel with this branch. And things that are in parallel have to have the same voltage. And so the voltage across this current source has to be 833.3 with plus up here and minus up here, minus down there. And so that's my voltage, and so my power, that's 100 milliamps, that's 0.1. My power is negative 83.33 watts.
What?
What? I was
So
making
what's your
I was making a pun, but you were really asking what?
so what? No, sorry. So what you're saying is essentially that because the left, right, and 100 milliamps is all parallel, that you could share the voltage over there to the 100 milliamps.
I'm not saying that I can share them. I'm saying that it is a fact that
Or is that they're saying?
elements in parallel have the same voltage. Anytime you have things in parallel, they have the same voltage. And this is a fact that you'll be using a lot. And so, like, if I have a voltage source here that's 6 volts, I know automatically the voltage across each of these resistors has to be 6 volts because they're in parallel.
I see.
Yeah, so things in parallel have the same voltage across them. And anything that is connected by a conductor has to have the same voltage, has to be at the same potential. So all of this has to be at a single potential because it's all connected by a conductor with no element in between. And everything down here has to be at the same potential, has to be at the same voltage. So everything here is at the same voltage. And so if everything here is at the same voltage, so this is some voltage, and everything there is at that voltage, and everything up here is at some other voltage, then the difference between here and here has to be the same as the difference between here and here. So you'll be using this later this semester when you'll be looking at capacitors and you're trying to figure out the voltage across the capacitor. A capacitor is not something you can use Ohm's law on. And what the easiest way to do it is if you can find some resistor that's in parallel with. And so if you can find the resistor that's in parallel with and you know the current across that resistor, then you can find the voltage across that resistor, and then you'll know the voltage across the capacitor. So you'll be doing that later this semester. All right.